Today I will be talking about boundary layers and boundary layer methods in some geophysical models. And this talk will be more or less, let's say, a complement of Isabelle Gallagher's talk on Monday, because she was talking mostly, as you might recall, about some problems in which you had domains with no boundaries at all. So I will focus on the boundaries. So maybe for some of you, what I will be talking about is well known and has been classical for a while. But I think that at least some ideas, even if they might seem classical, are not that well known actually. And so I wanted to talk a little about that, because it's a theory in which there has been some theoretical progress, or at least a theoretical framework about 10 years ago, something in which I had nothing to do. So I'm very glad to talk about it today. And at that moment, the limitations of that general theory were also explained. And so I have worked on let's say, precisely the limitations of that theory. And so this is also what I wanted to talk about today. So let me start with some introduction, in which I will give you some, I will present 3 problems that on which I will illustrate the whole talk, okay? And also give you some insight about what's going on. So the goal of this talk is to understand the influence of boundaries in some geophysical models, okay? And so there are many reasons for, as to why you want to do that. The first reason is that the geometrical aspects of your boundaries, of the coasts or of the topography of the ocean, might be important in some aspect. For instance, it is believed that when you have tides that go over the roughness of the topography, this might create some internal waves, okay, that then generate some energy transfer to small scales. The other reason is that you might want to have a qualitative description of your flow. And so you may want to know what happens close to the boundaries. Because, for instance, if you want to do some numerical simulations, then you want to know what the type of your grid should be. Okay? Are you allowed to take a rather coarse grid when you are far from the boundaries? What does far from the boundaries mean? And so on. Okay? So this is so that's the reason why you want to study what happens when you have small scales appearing in your problem. Okay? You want to find a way to average them somehow. So this is the first example I will be working with. It's the rotating fluids equation. So you have the classical Navier-Stokes equation, but with a small viscosity. So here I took an isotropic viscosity just to simplify the presentation, but you can have a different value for the horizontal and for the vertical velocity. Okay. You have a rotation term, and I took an F-plane approximation, so I'm assuming that the rotation vector is constant. So I'm looking at things around mid-latitudes, okay, in a divergence-free condition. And here, for the domain, I don't want to take into account the vertical boundaries just yet, but I'm taking boundaries on the bottom and the top of the ocean, okay? And this is what I want to study, okay? And so concerning the boundary conditions, at the top of the ocean, I take some forcing by the wind, and at the bottom of the ocean, I'm assuming that there is some friction of the velocity on the boundary. And the question is, what happens when the Rossby number is very small and when so when rotation is really large, and when the viscosity is small as well. So I won't be talking about the whole limit of this system. Okay, today I really want to focus about the boundary layer, so I won't be talking about the waves, the geostrophic limit, and so on. This is what Isabelle did in her talk on Monday. I will really be focusing only on the behavior close to the boundaries. So what is well known is that there are some boundary layers called Ekman layers that appear, and they're responsible for Ekman pumping, and they play a large role in the ocean dynamics because they allow for momentum and energy transfer from the winds from the wind to the, thank you. Okay, there. Merci. From the wind to the whole ocean, okay? The other thing is that because of friction on the bottom, there is some dissipation of energy on scales of order 1. So here I'm giving some references. I didn't, so obviously a lot of people have worked on this problem in many different communities. The references I'm giving here are limited to the community of people working in the theoretical analysis of PDEs, okay? And even in that community, I have not quoted everybody, so I apologize in advance for all the people who worked on that subject and whom I didn't cite here. This book, if you are a mathematician working in theoretical analysis of PDEs, is a kind of reference book on the subject in which you can find a lot of this stuff, okay? The other problem I will be looking at today is let's say an idealized Sverdrup model. So it's a 2D model. Here omega is, I didn't write it down, but omega is a 2D domain, which is arbitrary, okay? Smooth, but arbitrary. Psi is the stream function, and so here this model comes from an asymptotic analysis of, okay, a variation of the previous one, in which you have already looked at the geostrophical limits, okay, in a beta plane model, and I have neglected a number of terms just to. I can include them back. It won't change much what I'm saying, at least in some scalings. So what I have forgotten about is the friction on the bottom topography and the nonlinear term. Okay. So I'm looking at this PDE, and I'm wondering what happens when the small parameter epsilon here goes to 0. So again, something that is really well known is that there are boundary layers that appear on all the boundaries of the domain. They're called Munk layers, and again, they play an important role because they're responsible for the intensification of western boundary currents. Okay, so I will explain this in a while. So again, this is just some references of people who have worked on this subject in the theoretical analysis of PDEs. What was not so well known is that there are really some complicated phenomena close to northern and southern boundaries, and this is what we studied with Laure Saint-Raymond. Okay, and the third model I will be looking at is the Boussinesq system for stratified fluids. Okay, so here U is a two-dimensional function. Okay, B is so it's the velocity. B is the buoyancy. Here you have the Bruin-Väisälä frequency, and I'm looking at this in a domain omega, which is over a slope. Okay, so you have an angle gamma here. And this is omega. Omega is over this, okay? So this is x1, this is x3. I will keep this picture in the following. And the question that you're asking is what happens when all the parameters kappa, nu, and delta go to 0? So the situation is more complicated maybe than or at least it depends on more parameters than the two previous cases, so I will describe what happens later on. But the bottom line is, again, there is a boundary layer appearing here. Okay. This problem was suggested to us by Thierry d'Auxois after some work that he had done with Bill, I think in 1999, something like that. And so we studied this in a paper that appeared this year with Roberta Bianchini, who is in the room, and Laure Saint-Raymond. Okay, so all the problems that I just mentioned fall into a general framework, which is a theoretical one, which are singular perturbation problems. So I will give a definition that is adapted to the talk I'm giving here. Okay, I'm not claiming that it's a general definition or whatever. So what I'm in all the problems that I'm looking at, I have the following situation. I'm considering a PDE, okay, possibly linear, possibly nonlinear, possibly non-homogeneous with the source term and so on. So here I have a differential operator that has the following properties. It depends on the small parameter. It's of order D, which is bigger than 1. And if U epsilon converges towards U, in some strong sense, then the limit function is the solution of a PDE, which is of smaller, strictly smaller order. Okay, so for instance, maybe the simplest way of seeing that is on the second problem I was mentioning. If you look at dx psi minus Laplace and psi equals, I think I put some capital F here. Then, so it's a psi epsilon, okay? If you know that psi epsilon converges towards some psi bar, let's say in C4 of your domain, then you have dx psi bar equals 0, okay? So this here is my operator A epsilon. This is A bar. As you can see, A epsilon is of order 4, and A bar is just of order 1. Okay, so this is typically a singular perturbation problem. Singular perturbation problems are known to create a number of difficulties. And so today they are known to generate some small-scale structures, such as oscillations, and more specifically, boundary layers, which is what I will be studying today. Okay? And why is that? So on that problem, it's easy to see. When you look at psi epsilon, you have this operator of order 4. So generically, you can impose two boundary conditions for psi epsilon on the whole boundary. You can assume that the trace and the normal derivative of psi epsilon both vanish. Okay, this corresponds to a no-slip boundary condition for the velocity, so for the gradient of psi on the whole boundary. But for psi bar, this is not the case. Okay, if I impose that psi bar is so it's not 0 but f. If I assume that psi bar is a solution of this, unless the function f is very specific, I will not be able to assume that psi bar and its normal derivative both vanish on the whole boundary. Okay, I will have a loss of boundary conditions. And this loss of boundary conditions typically will create boundary layers. Okay. So the questions that I'm addressing today are the following. I want to look at the boundary. I want to find what the typical boundary layer sizes can be, what the profiles can be, and then ideally I want to construct an approximate solution of my problem and prove the validity of this approximate solution. Okay, and I will explain what that means. So now I will give you a general framework. This is so again, this is not something that I did myself, and maybe some of you think that it's very old, but I'm not sure that it's that well known, so I wanted to talk about it. So in all this part of the talk, I will assume that I have a linear problem, okay? So I have a linear partial differential equation with constant coefficients in a half space, okay? So a very idealized problem. And I will discuss the limitations of all these assumptions later on, okay? So I have this linear PDE, with some also linear boundary conditions that I'm not specifying for now. You can take Dirichlet boundary conditions if you want, but it depends on the order of your operator, obviously. And so my assumptions are the following. Each coefficient is polynomial in some small parameter, okay? The highest coefficients go to 0 when epsilon goes to 0, which, since they are polynomial, this is equivalent to saying that when I take epsilon equals 0, the highest order coefficients vanish, okay? And I'm also assuming that the problem is not completely empty, so at least one coefficient does not vanish, okay? So this is typically this case, okay? Here, all the coefficients of order 4 vanish as epsilon goes to 0, but the coefficient of order 1 is 1, okay? And so the goal is to have some asymptotic representation of the solution of that PDE. I don't want to find an explicit solution. I'm not interested in that, okay? Usually, you will not be able to find an explicit solution, but you don't really care. What you want to have is a good enough approximate solution, and a good enough approximate solution that is explicit, But the solution itself, I don't want to have a formula. I don't care about that. Okay. So I want to have an asymptotic representation of my solution and an error estimate. In other words, I want to construct this U epsilon app, which is explicit and which generically will involve a boundary layer. And I want to have an energy estimate telling me that essentially the difference between the actual real solution and the approximate one goes to 0. So actually, this is not quite true. Usually this is what is assumed, but in fact, this is not really what you want. What you want is to prove that the two are close. And close means that your approximation is relevant. Okay? Your approximation is relevant if you can prove that the difference between the two is much smaller than the size of either of them. Okay? Usually, you are able to compute, for instance, the size of your approximate solution because your approximate solution is explicit, so it's easy to compute its size. Okay? And so if you're able to prove that the difference between your real and approximate solution is much smaller than the size of your approximate solution, then it means that your approximate solution is relevant. Okay? Okay, this might seem like some very theoretical consideration, but in fact, for instance, in this problem, it's crucial to have that notion of energy estimate, because you will not be able to prove something like that, because the boundary layers are too singular. Okay. Before going further, I have to say a few words about a slight difference in point of view between the people who work in, like I do, in the theoretical analysis of PDEs and who use this kind of boundary layer expansions, and people who have worked with matched asymptotic expansions for decades now. Okay. In all the talk I will be giving today, the structure of my approximate solution will be the following. I will decompose it into what I call an interior part, which is the behavior of the solution far from the boundary, and a boundary layer part that has a strong variation close to the boundary. So here, this parameter, so xn is the distance to the boundary, if you want, and eta is the boundary layer size. Okay? And so the way that I see things is that here, so this u int might be, for instance, this psi bar. Like I said, it does not satisfy all the boundary conditions that you have for psi epsilon on the boundary. And so you introduce this boundary layer corrector to lift or to correct the boundary conditions satisfied by this psi bar. Okay? So the boundary layer correction must vanish far from the boundary. It decays at infinity. Okay? In the matched asymptotic expansions terminology, obviously, okay, this is strictly equivalent, but the point of view is slightly different. So you still have an interior solution, which is usually called the outer part of the solution. But what you are interested in is rather the behavior of your whole solution, okay, close to the boundary. And this is called the inner part of your solution. And so this is just the sum, obviously, of the two components. Okay, and then you match the inner part and the outer part when you are at a distance that is close to the boundary, but outside your boundary layer. Okay? So obviously, the 2 points of view are strictly equivalent. Okay? Yes? Yes and no. Yes, thank you. I will come back to that in a moment. They are equivalent in the sense that you just add or subtract your ints. Okay? They're not equivalent in the sense that I never said anything about the equation that is satisfied by the UBL here. I'm not saying that the equation satisfied by the boundary layer part is the same as the one in the original equation. Obviously, if you have a nonlinear term, then you have to be very careful to take into account the whole solution in the, thank you, Paula, in this setting. Okay, so, okay, so actually I might tell you a little story. This This played us a trick once with one of my co-authors because we hadn't paid attention to that in a paper that we did in which we had a nonlinear boundary layer and so on. And so we used that framework and we fell into this trap, exactly. Okay? And so as we were writing the paper and we were about to submit it, he called me and said, okay, you know, I just realized that in fact we hadn't taken into account the fact that since we are in a nonlinear setting, we had this. Okay, so we had to write then. So our paper was still valid in some specific framework, but then we had to do another paper to actually take that into account. But so thank you about that. If you have a nonlinear setting and you are using this framework, you really do have to be careful about taking into account this quantity here. Okay. So I think the reason why people working in theoretical analysis of PDEs prefer the first framework is that we like to use functions that decay at infinity because that we are trained that way. We like to work in Sobolev spaces, in L2 spaces, spaces that have finite energy. When we have functions that have a non-zero limit at infinity, we're always a bit stressed out. Okay? So the one exception that I know of is the Prandtl system. In the studies of the Prandtl system, people always use that terminology, the second one, okay, the Matthias syntactic expansion. But again, they are equivalent. You should just be careful about the nonlinear part. So the methodology that I'm going to talk about today was already developed by Eckhouse and Van Dijk, but it was put in a rather rigorous setting, and its limitations were really identified by Gérard Varenne-Paul in a paper that appeared about 10 years ago, I think. So you look for solutions. This is, again, my linear operator, and here I'm looking at solutions of an homogeneous problem, okay? And since you are in a setting in which you are in a half space, flat half space with constant coefficients, it's very natural to use, for instance, the Fourier transform and or the Laplace transform, and more generally to look at modal solutions, okay? So you look for specific. You forget temporarily about your inner solution, your outer solution, so your interior solution, and you look for specific solutions in this form. Okay. So here, this fractional u is just a vector. Okay. And I'm looking at this specific modal solution. So maybe I will illustrate this right now on an example, on the rotating fluids example, so that you know exactly what I'm looking at. So let's say that I'm looking at this system. Divergence of u equals 0. So in that case, I'm looking at some vector up, which is exponential of, say, I think in the rest of the talk, this is the convention that I took, minus lambda z. Okay? So here I have d equals 2, n is equal to 3, and I have a 4-dimensional vector, so my capital K is equal to 4. Thank you, David. And so what I'm doing is times some capital U.
Ah, okay. No. Yeah,
no, it's a constant vector. It's a constant vector, okay? And so you plug this into your equation, and what you obtain is a linear system, okay? So I will explain what my matrix A here is in this setting. So it's a 4x4 matrix. I will denote, okay, let me just give a name to the diagonal term here, which will be minus I omega for the time derivative, plus epsilon kh square minus lambda square. Okay, so this will be my diagonal term, so just a shorthand. So you will have this on the diagonal. Then you have the rotation. Okay, you have the pressure. 2 minus lambda. And then you have the divergence precondition. Okay? So in that case, this is by 4 by 4 matrix. Okay? And what I'm saying is that this is a solution of this if and only if the A applied to that vector u is 0. Okay? I want to find non-trivial solutions. So this equation here, which is a linear system, has a non-zero solution if and only if the determinant of the matrix is 0. Okay? This is just basic linear analysis. So at this stage, you're looking at the determinant of that big matrix, and you want it to be 0. Okay? What you want to find is the boundary layer sizes. So this actually gives you an equation on lambda. You have a big polynomial on lambda, which is of degree m. In that case, I think m equals 6. I will write down the polynomial in a moment. Okay? And that polynomial has complex coefficients, and all coefficients are polynomials in epsilon and xi prime. So there are a number of facts that you can infer from the analysis of polynomials in general and in complex analysis. So first, it has exactly m complex roots. Some of them might be multiple, but it has exactly m complex roots if it's of degree m. You're only interested in the roots that have a positive real part because, like I mentioned, you want to look at the solutions that decay far from the boundary. Okay? So you're only interested in the ones that have a positive real part. You know that as epsilon goes to 0, they all behave like some power of epsilon, which is actually a rational power of epsilon, times some vector. Okay? Then what you want to, in the end, the way I'm seeing it actually is that your boundary layer will lift some boundary conditions. So you might wonder how many boundary conditions you can lift with these boundary layers. So what you do is, so for each lambda, which is a root of that polynomial, okay, you know that that matrix has a non-trivial kernel. You look at all the vectors in that kernel, and the vector space spanned by all the vectors in that kernel, you look at that dimension, and boom, this is exactly the number of boundary conditions that you can lift. Okay, this is just linear analysis. And so the last point is that the boundary layer size is the inverse of the real part of the lambda. So obviously, you might have different lambdas that have a different size, so you might have a superposition of boundary layers of different size. Okay, this is I'm not assuming that the QIs are equal here. Okay, so what was proved by Gérard Varret and Paul, so about 10 years ago, is that as long as the QIs, so the exponents here of the lambda i's, are independent of xi, xi prime, okay, this is called non-degeneracy, then you can construct an approximate solution up to any order, okay? And so they have a framework in which they really prove, so I put quotes here, but this is an actual theorem, okay? It's just that there are a number of technical assumptions that I'm not writing down here, so that's what I didn't want to state a too complicated thing, but this is the general heuristic. So I talked a lot with David Gérard about that, and he told me that his vision was that this should not be a result that you apply as a black box, but it's really a kind of methodology that you can apply, and then you apply it case by case. Because in order to really have a proof, they need to have a lot of technical assumptions on their domain, let's say the regularity of the domain, the regularity of the coefficients, and so on. So, but this is the general idea. Okay, if you are in a non-degenerate setting, then everything will work out fine. So the limitations to this theorem are the following. So it needs to have constant coefficients and flat boundary. This is not actually true. In their setting, they have something for more general boundaries, more general coefficients, but I don't want to go into these details. So this is not an actual limitation, and I will talk a little bit about rough boundaries later. This only applies when the equation for the boundary layer is linear. Okay? So this is an actual limitation of that theorem. So again, at the end of the talk, I will give some insight about what happens when the boundary layer is not linear. And in my view, the most important limitation is that everything breaks down as soon as you have some degeneracy. Okay? So as soon as the QIs depend on the place of the boundary or the frequency that you're looking at, bad things might happen. And so this is typically what happens in this equation, and I will be talking about that later on. But before talking about the problems and limitations, let me give you some examples where this actually works really well. So the first example is this one, the rotating fluid system. So, okay, so I already did part of the computation. So this is what I wrote down here. So you have a system of order, a PD of order 2 in a three-dimensional setting. You have 4 unknowns, okay? So you have this big matrix, and when you compute the determinant of the matrix, you can trust me, you obtain this polynomial, okay? So it's a polynomial of order 1, 2, 3, 4, 5, 6 in lambda. So we have 6 complex roots. And as you can see, in fact, it is a polynomial of order 3 in lambda square. So you know that the roots are all plus or minus lambda 1, plus or minus lambda 2, plus or minus lambda 3. And so here what I'm writing down is in the case when omega is of size 1. I will comment about that later on. So as long as omega is of order 1, what you can prove is that there are 2 roots, well, at least actually 4 of them, that are of size epsilon minus 1, which correspond to the boundary layers, okay? And this is really the classical Ekman spiral. And one that is of order epsilon square. So this one you discard because it's not a boundary layer. The boundary layer 1 is really large, okay? So this one you can kind of discard it. And so you can leave 2 boundary layers that correspond to this lambda 1 and lambda 2. The one point that I want to make here is that I'm not assuming anything a priori. I'm not saying, okay, the pressure doesn't vary in the boundary layer, so I discard the pressure term, I only look at the other ones and so on. I keep all the terms in the equation, and okay, you might say that this is dumb because it leads to more complicated computations, but actually in some cases it's important to keep everybody and not to assume anything on the system, okay? So, and these, the fact that you can only leave 2 boundary conditions instead of 3 is responsible for the Ekman pumping in a way, because then you need to add some corrector that will lift the 3rd boundary condition, and this corrector will precisely be the one that leads to some vertical velocity of smaller order entering the fluid. And so I cannot see the last remark, but I guess that the rest of you can. So if you assume that omega is actually of order 1 over epsilon, which is what occurs or what is relevant when you look at the waves for that system, okay, then you have additional issues when kh is close to 0 or when omega is close to plus or minus 1 over epsilon. So this is what we studied with Laure. This is typically a degenerate case, okay, in the definition that I gave one slide ago. And this is typically a case in which you have to keep everybody. In that case, you need to keep the pressure term because it plays an important role in the boundary layer size. And in that case, the boundary layer sizes are not the same. Okay? But, okay, this is a case that was already well known before all this theory appeared. And so now, as a second example, I want to talk about the critical reflection problem for internal waves. So in this domain here, so now here, this is the x I'm looking at, and this is z, okay? It's a normal component. So again, you have d, so the order of the PD is equal to 2. You have 1, 2, 3, 4 unknowns because you have 2 components for u, 1 for b, 1 for p. Okay, So the matrix A will again be a 4 by 4 matrix. I'm not writing it down because it's a bit tedious, but okay, you can do the computation. And so we can look for solutions of the linear problem in this form. Okay, and what you find is that lambda is the root of a polynomial of order of degree 6. I won't write down the polynomial because it has a complicated expression, but I will give you the results in the next slide. And an important quantity is the criticality parameter, which is this zeta, which is the difference between the sine of this angle and omega, the frequency. So why is that? This is because, so I think this is actually in the case when n is equal to 1. It's because what you're looking at actually is the reflection of, so you have an internal wave, an incoming wave, which is arriving on your wall here with a given angle, okay? And what happens is that you will, the wave will reflect on the wall, and the law of reflection, as many of you might know, is a bit specific. What is conserved is this angle, okay? So here I'm always dropping things in the critical case. So this angle here is preserved, okay? If you have no viscosity, no nonlinearity, what happens is that this wave is reflected like that, and this angle is equal to that one. Okay, so if you are in the case when this angle is equal to the incoming angle here, then you see that you really have a strong focusing close to the boundary, and this is what the critical reflection problem is. And so what we found was the following. So I'm assuming that nu and k are of the same order, and to simplify things, I'm assuming that kh and omega are non-zero. So zeta is my criticality parameter, and what you can prove is that there are always 3 roots of the equation, the polynomial in lambda, that have a positive real part. And then you can classify the type of boundary layers that you get depending on the size of zeta. So I will first describe these 2 cases, and then I will look at the intermediate one. So if zeta is far from 0, so if you are not in a critical reflection regime, then you have a reflected wave, okay, like in the inviscid case, and you also have a boundary layer that lifts 2 boundary conditions, and the size of this boundary layer is nu to the 1/2. Okay, so that you can lift 1 boundary condition thanks to the reflected wave, because the reflected wave will lift, say, the vertical component, and then the boundary layer will lift the other 2. If you are in the critical regime, which was the regime that it was described by Doxois and Jung in their paper, you have a superposition of 2 boundary layers. You have 1 boundary layer, which is like nu to the 1/3, that is lifting 2 boundary conditions, and then you have a smaller layer, which I think was not described in your paper, which is like nu to the 1/2 that lifts the remaining boundary condition. So a way to see it is that actually this boundary layer takes care of the conditions on u, on the velocity, and this one, more or less, it's not completely true, but it takes care of the boundary conditions on b. And then in the intermediate regime, well, you have a transition between these 2 cases, this case where you have only 1 boundary layer of this size, and this one in which you have 2 boundary layers, and you have either 2 or 3 boundary layers that have different sizes, okay? So you can really follow the behavior of each lambda depending on the parameters, okay? Okay, and then what's the next step? So once you have a good understanding of the behavior of the boundary layers, you can try to, so you can construct a generic boundary layer given arbitrary boundary conditions. You can try to build an approximate solution with the interior part, which I did not describe in this talk at all, okay, and the boundary layer 1. So the role of this approximate solution is, so the role of the boundary layer is that the approximate solution will satisfy exactly the boundary conditions with no error at all, but obviously it's not an exact solution of your equation, so there is a small remainder. Okay, and then you write an equation for the difference, you perform your favorite energy estimates for your problem, and typically you end up with something like that. So I wrote it in a rather abstract way because I didn't want to consider every single case, but typically you prove an error estimate on the difference depending on the size of the remainder. Okay, So if you are, for instance, in that situation, then x will be L infinity in time, L2 in x. Okay, this is the measure of your energy. And C epsilon might be a positively negative power of epsilon. And if you want to have a good approximation, then this error here, which controls the size of the difference, okay, must be much smaller, like I explained, than the size of your approximate solution. Okay? But because of the singular perturbation, you might need to construct a lot of correctors to be able to do that. Okay? So it's not always that easy. But in all the cases that I presented, this is something that you're able to do. Now in the... How much time do I have left?
No, 10 minutes.
Ah, okay. Okay, okay. So in the remaining time, I will explain how you can go beyond the general theory. And, yeah, and I will start with what I said was, in my point of view, the most important limitation, which was the non-degeneracy assumption. So I'm looking at this problem here, okay, and I'm looking at it in an arbitrary domain. And by arbitrary, I don't mean I'm taking a stadium. I'm saying, so this is the typical domain in which problems arise, but actually problems arise. So you might say, okay, but actually no, it's fine because no ocean basin looks like that. But in fact, as soon as you have a domain, for instance, that is non-convex in the x direction, or as soon as you have islands, you have exactly the same type of problems as with this stadium here. Okay? So let's say that this is the typical domain I want to look at. And what you can keep in mind is that actually what I will be stating works for any smooth 2D domain, even with islands. So I'm distinguishing between 4 parts of the boundary. The north and south parts are the one in which the angle theta, I don't know if you can see here, but I'm denoting by theta the angle between the normal and the EX vector, so the east-west vector, okay? So this is my angle theta. When that angle is equal to plus or minus pi over 2, I'm calling this the northern and southern part of the boundary. And, okay, obviously this is the eastern part and this is the western part of the boundary. When you apply all the analysis that I just did, what you find is that there are boundary layers on the eastern and western sides that are of size epsilon to the 1/3, and epsilon actually divided by the cosine of theta to the 1/3, because you have a balance between this dx derivative here that makes a non-zero, non-pi over 2 angle with the normal, okay? And this higher derivative here, okay? But obviously, as cosine of theta goes to 0, this goes to infinity, and so you have a degeneracy of the boundary layer size. Okay, this is the textbook example of boundary layer degeneracy. And on the other hand, on these 2 parts of the boundary, then the dx is really tangential to the boundary, okay? And so in that case, this will not give you any boundary layer behavior, and so you have a very different behavior for the boundary layer size here. It will be like epsilon to the 1/4, okay? And so then on these 2 parts, you can lift 2 boundary conditions. On this part, you can also lift 2 boundary conditions, and on that part, you can only lift 1. This is linked to the to this boundary layer analysis and to what I said previously. So I don't want to go into the details, but it's really it's linear analysis. Okay. What happens is that on this boundary, you always have 3 roots, but 2 of them correspond to exponential modes that grow, and so you discard them, so you only have 1 left. And here you have also 3 roots, but 2 of them correspond to exponential modes that decay, and so you keep them, and 1 corresponds to an exponential mode that grows, so you discard it. Okay, so we can lift 1 boundary condition here and 2 there. So as a consequence of this Foreman analysis, what you expect is that the interior part will satisfy this equation. Okay, this is the one that I wrote earlier. And because of this, you need the interior part to vanish on the eastern boundary. And so this is responsible for what is actually observed in practice, which is the Western intensification of currents, okay? So the velocity, which is the orthogonal gradient of the stream function, will be very large in a small boundary layer close to the western boundary. So this is, for instance, what happens for the Gulf Stream. But because of the degeneracy, you cannot apply the black box, say, the Gérard-Varret and Paul theorem, and so you have to do something else. And so the analysis is really quite technical. What you find is that the sizes of the boundary layers are the ones that are predicted by the formal analysis, okay, so something remains true, but the boundary layer profiles are not. And so on this part and this part of the boundary, you don't have an exponential profile at all. Okay? What you have is really the equation on that part of the boundary, or if you have, for instance, if you have an island, close, you will have a discontinuity boundary layer in the vicinity of these parts. Okay? And they really satisfy an evolution equation, so they are not intrinsic. Okay? So you can compute them numerically, but you don't have an explicit expression. Okay? And you have a complicated superposition in the transition zone. So in these zones, close to here and close to here, you have a rather complicated superposition of both boundary layers. And what you shouldn't do, which took us a while to figure out, and I think the theory is a bit misleading in that way, is that you shouldn't try to connect the boundary layer sizes. Because if you follow that theory, you might be tempted to say, okay, but that lambda is actually smooth functions of all my parameters of, for instance, the abscissa, the curvilinear abscissa along the boundary, something like that. And so you might be tempted to say, okay, I'm following that lambda. It changes sizes abruptly, but that doesn't matter. Okay, this is absolutely wrong. If you do that, you create very strong singularities in your approximate solution, and this leads to nowhere. Okay, so what is connected is actually the amplitudes of the boundary layer, but not the sizes. Okay, so when degeneracy occurs, you still can perform an analysis, but it's really in that case you have no general theory. I think you have to do a case-by-case analysis. And, okay, so you shouldn't rely too much on the general theory that I presented, because it might give you some wrong intuition, actually. Now I will talk a bit about rough boundaries. So in what I will be talking about here, let's assume that you're looking at that equation, for instance, in a domain omega, which is, say, x3 is greater than epsilon times some gamma of xh over epsilon. Okay, so you have a boundary here with amplitude of over epsilon. The typical variation scale is epsilon. Okay, so this is your boundary, but it's not flat. Okay, it has small variation. And if you perform the analysis, so in that case, the boundary layer size will be the same. The boundary layer equation will be elliptic and so on, but you will be close to a rough boundary like that. And so okay, the previous theory does not apply at all, but you can still keep parts of it. So what you do is the following. You introduce an artificial boundary above the bumps of your rough boundary, okay? Above that artificial boundary, you can still perform Fourier analysis and so on. And so you can do the classical resolution that I presented earlier, okay? So, and you can define a connection operator between the two parts of the boundary to define a kind of transparent boundary condition that you will use later on. And then you can, in that lower domain, which is bounded in that direction, you can solve your equation using the transparent boundary condition. So I won't say much more about that. So the important thing is to define a good transparent boundary condition that is adapted to your problem and that relies on the analysis in the flat above half space. Okay? You don't need to assume any type of structure on the boundary. So in particular, you don't need to assume that it's periodic or quasi-periodic or anything. You can do it for an arbitrary boundary. So this type of idea was initiated by David Gérard-Varret and Nader Masmoudi, and then we used it in a number of papers. And there's a work so mostly for Ekman type layers, say. And this was done, say, recently by Gabriela Lopez-Ruiz for, let's say, Munk boundary layers close to a rough boundary. And I will conclude by talking about nonlinearities. So I will remain very, very vague here. So I will distinguish between several cases. So the first, easiest case is the case when the boundary layer equation itself remains linear. In that case, everything that I said remains true. Okay? The only thing is that the nonlinearity might affect the energy estimate. So in fact, in the examples that I presented, you actually had a nonlinearity, but the boundary equation was nonlinear, and still we are able to prove a result. Okay? It's just that the nonlinearity will, for instance, limit the time of validity of your approximate solution. So this is really the easiest case. When the boundary layer equation becomes nonlinear, then what I just said might no longer apply. If it's semi-linear, so if the nonlinearity is of lower order, then generically you can still build a solution. Okay, you do a kind of a fixed point for small data close to say a linear solution. So we can still use the linear theory to construct a solution in semi-linear cases. But if the boundary layer equation becomes really nonlinear, like the Prandtl equation, so if the nonlinear terms are the terms of highest order, then okay, what I just said does no longer apply. You really have to do something else, and it's a case-by-case analysis. Okay. So what I just did was present a general method to construct linear boundary layers, mostly near flat walls. So it really relies on a linear analysis, and I think it's really beautiful, and we should use it when we can. Obviously, it has limitations, but it can be extended to semi-linear settings or to non-flat walls in certain regimes. I think its main limitations are the degeneracy issues and the genuine nonlinearities in which you really have to do something else. Okay, so I will stop here.
Thank you very much, Anne-Laure. Questions? Yeah, Paolo.
So the point about the degeneracy when you go from the western to the northern side or the southern side, I think it's because your approach uses Cartesian coordinates, because the typical treatment of those corner boundary layers in meshed asymptotics is to actually go to polar coordinates.
Oh, that's what we do. We use local coordinates. Our coordinates here I presented everything in the case of a flat boundary, but in the analysis that we did with Laure Saint-Raymond, obviously our coordinates are the distance to the boundary and the curvilinear abscissa. So they are really local coordinates.
Okay, but because usually that cures the corner problems. That gives you
actually, corners are okay. Corners, this type of domain is easier than than this one. This one is okay. But actually, having a continuous transition between the between this boundary and this one is much harder.
Yes.
The original version of this problem was by Stommel, not Munk, and the difference is that he had only a single Laplacian operator.
Yes.
Is there some reason you picked the more complicated one as your main example with the double Laplacian, I think?
Well, this one, I think this one comes actually is really the one that comes from the the actual viscosity, okay? Because Laplacian psi is omega, right? And so the bi-Laplacian of psi is Laplacian of omega. So this is actually the equation in vorticity form.
That's correct, but I think...
and then you do have an additional term with a Laplacian that comes from friction. You can do the same analysis with a Laplacian, and it doesn't change much. The conclusion is the same. The only difference is the boundary layer equation that you get on the north and south boundaries. But other than that, you have essentially the same technical issues.
Perhaps there's an interesting thing when you add the nonlinear terms, which have 3 derivatives.
Yes.
And then in the Stommel problem, they have the most derivatives. And
Definitely.
but in the Munk. Yeah.
Yes, and I tried to do some computations about that, and I really don't know what happens. I think as long as you can look at the nonlinearity on these boundaries, and that's okay. But as soon as when the nonlinearity plays a role in this part of the domain, I think it's very complicated, and I don't really know how to handle that.
More questions? Yes, Michael.
I just want to say that in some calculations with a simplified GCM, we noticed indeed for that problem that Paola Cesi told us we should forget about, that there are some interesting things happening in the northwestern corner of the domain. So maybe you want to look further for some irrelevant problem.
So I had the questions about your last comments on the nonlinearities. Mm-hmm. Can you maybe draw, because I don't understand this difference between the 2 subcases. So
okay, so
some visual example of it.
I don't know about visual. I can I can write an equation. Okay, so okay, for instance, in that case, the Ekman layer equation will be in that. So in rescale coordinates, okay. So it will look like that. So it will be minus Laplacian u plus u grad u plus E3 wedge u plus gradient of p equals 0, divergence of u equals 0, okay, and u on the boundary. So in that case, this is typically the type of case where you have to be careful between matched asymptotics and so on. So here I'm assuming that u is 0 on the boundary, and I have a far field condition. So the limit as x3 goes to infinity of u of x equals something. Okay. In that case, what you can do is say, okay, you see here I have 2 derivatives, here I have just 1. And so you can essentially treat that term as a perturbation. Okay? And if you treat it as a perturbation, you can do some kind of, for instance, here if the limit is 0, okay, I have an obvious solution which is just u equals 0. Okay? So if the limit is small, I can treat that term perturbatively because it's nonlinear. And my solution will be a perturbation of the linear one. That's the idea. But this works essentially as long as you don't really perturb the linear analysis. And one requirement is that the number of derivatives here is smaller than the number of derivatives that you have there. I mean, it's not a general theorem, but it's okay. And for instance, if your equation became, I don't know, something, if you didn't have that, but if you had this, then this would lead to an actual real, so this is not a very good, okay, but something like that, then it will be an actual true perturbation of your, of the linear analysis, and then I wouldn't know what to say.
So let's thank once more Anne-Laure. And